Hey, so I'm James. I'm a security researcher at Red Balloon Security, and I should mention when I was doing this research, I was working at NCC Group, and they were nice enough to let me still present it after I quit. But I'm going to be talking about hacking Amiibo, and if you're not familiar with Amiibo, there are these toys for Nintendo consoles, and what you do is you take the toy, you get some toy, and you can put it on the console in someplace, and it interacts with the game. So like in one of the first games to really make a big use of this was the Super Smash Brothers game, and like you would get some character, and then when you use the toy in the game, you get that character as like an AI, and you can save, you could train it and save items to it. These devices actually, you can read and write data to them and save, so that each game can save its own data onto the Amiibo. And the way that works is that they use NFC. So in the bottom of the tag, there's something. It's kind of like an RFID. There's an NFC tag, which is NFC is a way to do contactless data and power transfer. And what basically all it is there's big. It's small, but there's an antenna and then a very tiny integrated circuit that gets powered by the radio and also can there's actually it can do logic and yeah. Okay, so also around the time when I started doing this, I was really into save game hacks, and one example back on the Wii was for the Twilight Princess game. One of like the only two string inputs in the game was vulnerable to buffer overflow, and that was when you could name your horse. So they edited the save file and did a basic stack overflow, and using that, they were able to do a software-only kind of jailbreak on the console and install new apps onto it. And so this is what it looked like. They just have this file. You load it up. You walk up to some character, and as soon as you talk to them, the buffer overflow triggers, and they run their own program and install their own channel on the Wii. So the reason that you do this is that modern consoles. Or the past few generations of consoles, they are kind of like smartphones in a way where they kind of lock you out from having total control of the device. So people that want to say if you wanted to run your own homebrew games or you want to run Linux on a console or something, that you wouldn't really be able to do it without breaking the security model of the console. And they've been getting very complex and very interesting. So there's a diagram here of the 3DS, which took about like 4 or 5 years to break because and you can see there's so many steps and there's all this encryption and signing. So part of the reason you want to find an exploit is you can use that exploit, you can leverage that exploit to jailbreak the console. I also started this before the Switch was coming out. So there's only the Wii U and the 3DS, but we knew that the Switch was going to come out and it was also going to be supporting Amiibo. So basically anything that I would work for, so if I'm hacking these and I can do something on the 3DS or the Wii U, it's also going to work on the Switch when that comes out. And it'd be interesting to see like these new games on the Switch that are going to save all this Amiibo data on them if I could maybe find an exploit on the Switch doing that. And like it's not the most practical attack, but it'd be like a very hilarious thing to do to find some attack where you use an Amiibo to exploit the Switch. So the questions are like how easy would it be? How easy is it to clone the Amiibo or spoof them? Could the data on them, could we use that for some kind of save game exploit? And finally, for especially, could it be used for an exploit on the Switch? Those were the questions I had in mind when I started doing this. So to get started, the first thing that I'd want to do is see what the data on the Amiibo is like, and if you actually get a scan or a dump of the NFC tag, it looks like this, and it's mostly indecipherable bytes, and it's mostly encrypted. So it turns out part of this is actually in plain text. So if I go through the different parts of it, some of the things that you can see are that the serial number is right at the beginning, and that's in plain text. There's actually a character ID that's also in plain text. That's a few bytes long. But the biggest chunk of it down at the bottom is all encrypted data, and then some of the other stuff in there, besides some settings, there's signatures and hashes for the encrypted data. So almost all of it is protected by encryption and signing, which means you can't tamper with it because you're not going to be able to make a valid signature. So the first part, if I want to actually edit these and mess around with them, I'm going to have to figure out how the crypto works. To start off with, and at least know that they're encrypted, and also that each one has a unique encryption keys. So it's not like you can't use the same keys for every single one of them. Also, due to the way they're signed, you can't directly copy data from one Amiibo to another. The signatures actually involve the serial number of the Amiibo. So, and it's going to be very difficult to do anything with them until you can break the crypto. So one person had actually already figured this out, and they released this tool called Amiibo tool, and this would actually go through it would do the decryption and encryption algorithm, but you need the keys to do that. And one thing that they would not do is release the keys because they don't want to get in too much trouble, and they also don't want to really aid people in piracy. So if you want the keys, you're going to have to find them yourself. And the alternatives to just having the keys to use with the Amiibo tool, I think the same person also made an online API that you could use if you get an API key from them, and like you could send your Amiibo data to their server and it would do the crypto for you. The issue with this is I would be limited to so there would be kind of a rate limiting, or if the service goes down or if they don't like what I'm using it for, I wouldn't really be, I'd be restricted by that. And there's also these little cheat devices. So if you just want to copy your edit Amiibo, you can get these at GameStop, and they kind of do the same thing where it has to be connected to your PC and it has to be online, and they're just going to send your Amiibo data to their server and then do the encryption or decryption there, and also the editing there, and send it back to you. So they're also, you can't just use this to do whatever you want either. They're not really trying to help you get the keys to do this yourself. They just want you to buy their tools. So the next part. So the first part is to do anything really. I'm going to have to find the crypto keys and to use with the Amiibo tool. Next is when I have that and I can edit the data. How am I going to actually simulate? So kind of send whatever Amiibo data I want to the console, or simulate them. And the answer, because it's an NFC device, one of the main tools for doing NFC or RFID research is called the Proxmark 3, and it's this software-defined radio tool. All the code for it is open source, and you can reprogram it. So if I wanted if I needed to add new behavior to it, I could do that by writing more code. And the other nice thing is that this could be used. It can simulate the Amiibo and act like an Amiibo to the console. It could also simulate the console and act like a console to the Amiibo. So for any steps that I want to mess around with, I'd be able to do that with the software-defined radio. Just to go over what the NFC tag is again, there's basically the digital control unit. So this is what takes in commands and will send out the responses, and then you have a little bit of EEPROM storage, and then RF interface just so it can communicate over the radio. The Proxmark already has some built-in support for the basic part of this, where it can simulate an NFC tag that wakes up and reports what its serial number is. But beyond that, it doesn't do anything else. Almost all the other code on Proxmark is for messing with proximity ID cards. So to simulate the specific kind of tag in an Amiibo, which is called a NTag, we'd have to write new code to simulate that. And this is from the datasheet on NTag. So basically, the part on the top that's in green, that's where the tag will wake up and show its ID, but everything in the bottom like reading data, writing data. There's a password authentication. There's version and reading signatures. All that stuff would have to write new code to simulate that on the Proxmark. So get a useful tool to actually start tampering with Amiibo data and like maybe trying to do exploits against games or the console, you'd have to first implement the NTAG 215 simulation with some software-defined radio, like the Proxmark, get the crypto keys to actually be able to change the data, and finally kind of glue them together in a way that you have like a useful tool where you can tamper with the data, send it out to the console, and get some feedback, and come up with some way to use that to like do kind of fuzz testing. So the first part I looked at was actually getting the crypto keys. So like I said before, some of the people that already figured this out didn't want to release the keys. But luckily the 3DS was already jailbroken at this point, and by getting a jailbroken 3DS, it would be much easier to go through the process of just reverse engineering the NFC service code on that device myself, because the years of work that the other people put in the jailbreak it was already done. That was like the hardest part. So at that point, I can just dump out the NFC service binaries and start like trying to can I find the crypto keys in here, and also I can kind of tamper with those processes while they're running on the device. So there's this cool custom firmware for the 3DS that I used. It's called NTR, and one of the cool things that it would do is add a debugger onto the 3DS. But sadly, for the version of 3DS that I had, at least breakpoints in the debugger didn't work, which means I can't just like step through the code and kind of watch what's happening as it's going. Really, all I could do is read and write memory out of the different processes on the 3DS. So this is what the interface for it looks like. So you connect to the debugger. You could list out processes, and then you can also read and write from memory. And ideally, there's this debugging feature that you could turn on. But as soon as I turned on as soon as I attached to a process to try to debug it, it would just crash the 3DS. So I was kind of limited in what I could do with that. But one of the things that I can do just by dumping memory is see if I dump out. So, well, for one, dump out the service and see like what's inside it. But two, if I use some program that actually will read an Amiibo and do something with it, and cause the NFC service to decrypt it, and then I dump the memory out immediately afterwards, I might be able to recover the decrypted images that way. And that was one of the first. So one of the first things I did was I set up a custom app that would turn on the NFC service. It would scan, it would wait for the Amiibo to show up, and as soon as it would read it, I would use the dump memory feature in the debugger, and then I could search through it and try to find my decrypted data. So you can see here kind of that there's like the plain text nickname that I had written, and also like the name of the me that it was set up with. With this way, at least, like I can start to get the decrypted images and see what's inside them. Although it's a very clunky way to do it, but to go over what we can see now. So there's the nickname, information about the me that it was registered to. There's the biggest part is the game or application data and the ID for the application. So any game can save whatever data it wants into this game data section. So whatever the last game that you played with that did this is going to have its data on there. There's the serial number again, and the character ID, and also a signature, and then just more signature and settings bits that are kind of less interesting. So when it came to doing like a reverse engineering the NFC service, one of the first things that you kind of do with any binary is search for strings, that you try to get some context for what you're looking at. And immediately, like just doing a simple string search, found this really weird Uh, really suspicious-looking strings. And one of them said locked secret, and one said unfixed infos, and like there weren't really many other strings at all in the binary. So this stuck out right away, but I didn't know what it was yet. And there's actually two sets of this, like unfixed info, locked secret showing up. And wanted to figure out like how these were used. I had some other issues where I was trying to I wasn't using IDA. I tried using Hopper on Linux, and it didn't work too well. But one of the issues with looking at the NFC service is the code isn't set up like a typical program where you have the main entry point and it calls into all the other parts of the app. It's set up as a service where there's all these little stub functions for the different service calls you can make, and like little isolated bits of code. So when you identify, like for a typical program, you identify like some main entry point, and then the disassembler can like kind of trace the path through all the code and like keep identifying more stuff for you automatically. But this way, I had to like manually go in and see like, does this look like a function prolog in hex, and then like hit the code analysis thing and turn it into code. And so it was very bad, like slow process to work with in doing the static analysis. It also crashed a lot. So I have like a broken debugger and like all this hard to identify code, and my disassembler I can't search without crashing half the time. So what can I do in this situation? So what I decided, or what I ended up doing, was using the custom application and the homebrew libraries that already existed. What I would try to do is leverage them to call into certain parts of code and then identify where that code was in the binary. So there was this code. There's these error codes that would show up a lot, and if you called a certain function like open app data or scan tag or whatever, and you called it at the wrong time, you'd get this invalid state error code, and it shows up like kind of all over the place. It's this nice like unique looking 32-bit value instead of just being like a 1 or a 2. And what I did was I could search for that error code throughout the binary, and the first thing I did was I'll just replace that code with like hex deadbeef, and then start calling random functions. And when I see the deadbeef show up, I kind of know like that I called into that piece of code in the binary that I had changed. This is where I had like added more features into the app, so I could call all these different service calls and kind of do them all at the wrong time and try to do it when I would be in the invalid state. The second iteration of that was instead of like putting deadbeef, I would put the actual address in the binary that I had replaced. So when I see an error code that shows up that's not the original error code, it's actually giving me the address to look at in the binary to see like what I had called into. And then I could just start pressing more buttons, like doing things at the wrong time. And if it was in the invalid state, it would return an error, and the error would tell me where to look in the binary to find that code. And the last iteration I did of this, and the best way to use this is instead of just replacing the invalid state error codes, I would take a list of all the different functions where I might want to where I wanted to see where they were. I would rewrite the beginning of the function so that it would immediately just return its own address as an error code. And then now when I call stuff, even if it's like not in the invalid state, it doesn't matter when I call it, it will immediately just give me back an error code telling me what the address is. So like if I call the open app data, I immediately get an error code, and it gives me the address of open app data in the binary, which will help me reverse engineer that, and like it gives me the context I need to understand what's happening in that assembly. And this is a video of the app. Okay, well, That's what I get for not doing a live presentation, or demo, I mean. Okay, but okay, all that happens is I rewrite the function paralogs, and then like you see here, the get Amiibo settings is instead of returning the invalid state error code, it's returning its address. I go into Hopper, and I go to that address, and I have identified where that function was in the binary. So it's now I can much more quickly find my way through the NFC service and start to like focus in on trying to find where the cryptography functions are in the binary. So then what I start to eventually, from there I actually start to find there's some function that reads the weird unfixed info lock secret strings that I had seen before. And it does, if you remember, there were two sets, there were like two copies of that. So there's, when it reads these values, there's actually a conditional statement that chooses which set to read. And it reads some weird bit from memory to make this decision. So I looked up what this bit means, and it's actually something that's set by the kernel, and it's some configuration settings that are set by the kernel. And there's this bit in here that tells you whether the console is a developer unit or a retail unit. So at this point, I know it's like I already knew there's different sets of encryption keys for retail consoles and the developer consoles. So at this point, I was pretty certain that this unfixed info lock secret stuff was the keys needed to do the encryption for the Amiibo. And then I found another thing that was, if you look up the algorithm for doing HMAC, this function matched exactly, like you could tell it was doing an HMAC, and also by tracing what the input to it was, I could see part of that unfixed info blob was being used as a HMAC key, and I could, so at this point I can kind of see like how different parts of that crypto information is being used. And also I can start to see kind of where like there's stuff in the binary that looks exactly what the MeTool program does. But I wanted to get the keys as quickly as possible. So now knowing that I had at least part of it, I started searching for like the parts that I had online, and actually found, by searching for them in a certain format, I found the whole file that was needed for a MeTool, and then I could do the encryption and decryption then, which was nice. But I looked at what was inside this file, inside the key file, and there was stuff in there that did not appear at all in the NFC service binary or anything else that I looked at, and I wanted to know where it actually came from, so I could understand how the whole system was working. So what the big piece that hasn't shown up at all yet in this is the 3DS had this complicated AES encryption dedicated hardware that was explained in like a really good talk called Breaking the 3DS at CCC. And what happens is there's these two different key components that get sent into this hardware AES engine, and then they are scrambled to generate a new key, and that new key can never leave the AES chip. The only way to use it is you tell this chip what you want to encrypt, and it will do that for you, but you can never access like what the real key is being used inside there. So at the Breaking the 3DS talk, they figured out what that algorithm was to generate the composite key, but before that had happened, before they broke that, the way that what this engine would do, it was using AES in something called counter mode, and with counter mode, you have some initial counter value and a nonce, and it uses the AES block cipher to encrypt. It encrypts the counter and generates a block of kind of pseudo-random data. And it keeps increasing the counter and making a new block by block. And then once you have enough blocks to cover whatever your input is, it will do XOR encryption with the blocks against your like say your plain text, and then you get the ciphertext. So an important part of the XOR operation is if you XOR something with 0, you just get the same value back. So if you were to tell this AES engine just to encrypt all zeros, what you're going to get back is the intermediate key stream. And using that, you can, which is kind of, they refer to it as a XOR pad. Using that, you can actually do the offline encryption and decryption without needing the AES hardware. And this turns out that this was that weird value that was in the key file that I couldn't find before. And to verify that, I just kind of set up like a Python script to take different values from the info I had and try to do AES encounter mode. And it turned out using the AES parameters from the NFC service binary and using some NFC key info from the 3DS, and you encrypt. I just encrypted a bunch of zeros, and I got something that matched this this weird 32-byte value that was in the MeTool key file. So now, putting all those parts together, you can start to actually explain what the entire system is. So on the NFC tag, or on the data on the tag, there's two partitions to the data that's on there. There's the locked secret part is the tag information, which is like the serial number, the character ID, and then just a kind of unique 32-byte value that's unique to each Amiibo. And then the other section, it's called unfixed infos, is the data. It has like settings, it has the game data and the registered me data. Those are all in the data section. And for each section, what happens is they generate two sets of the AES parameters and HMAC keys. And then for each partition, the HMAC key that was generated for it, they sign that partition. In the case of the data section, they encrypt it with the AES. The tag section doesn't get encrypted, that remains in plain text. And then finally, they kind of rearrange that whole buffer to the format it needs to be on the NFC tag. So to reverse that, they rearrange the buffer again, generate the keys, decrypt the data, and then check all the HMAC signatures are valid. So the most complicated part of this is actually generating the AES parameters and generating the HMAC keys. So the way that they do this, they use a deterministic random bit generator, and the seed for the random bit generator is going to take the type string, which is the name of the partition. So that would be what the locked secret or unfixed info string is. That's the type string. Then they take some magic bytes that go with that partition. And in the case of the data partition, excuse me, they also include the write counter, which is the number of times that tag has been updated. Then they put in the serial number of the tag, and finally the encrypted 32-byte value, which came from the unique 32 bytes in the tag section, getting encrypted through the AES hardware engine, and like putting all that stuff together. That's the seed for a random bit generator, and what the bit generator outputs is 48 bytes that are going to be a new AES key, AES counter mode parameters, and another HMAC key. So this output is the unique keys used on the Amiibo, and also in the case of the data section, because the write counter is part of the seed. Every time that you update data on the Amiibo, there's a new set of keys that are going to be generated. So it's not just unique to Amiibo. It's each Amiibo. The keys are unique to it in its current state. So the keys keep changing every time you update it. So that's the crypto system. So the next part, having that now I can like edit, put whatever data I want in the Amiibo and try out in the game. But to do it in a convenient way, I have to set up the Proxmark simulator. So the process behind this is basically the Proxmark can sniff traffic. So one thing I would do is put the Proxmark between an Amiibo and the console and record all the traffic. And even though Proxmark doesn't support simulating all these things, it is pretty good at actually identifying what the different commands are that it's seeing. And also I can use the datasheet for the end tag to an X to also help like identify what traffic I'm seeing there. And I can go through the whole process of like how the console will read from the Amiibo and kind of build that up in the simulator. So to go over again, the stuff that I need to implement for the end tag simulation is I'm going to have to implement like the read commands, the write command. There's something called conversion. There's a password authentication and read signature commands. And then finally, in addition to just interpreting the commands, I also have to set up some piece of memory on the Proxmark itself where I can store the data that would be on the NFC tag, which is not something that was like already set up in the code yet. And there's no developer documentation for developing on Proxmark, so you just kind of have to read through it and like figure out where everything is and figure out how it works yourself, and then where to add stuff. So what I had originally, what I'd like to do is like make a new generic end tag simulator thing that would be nice and modular, but I ended up just kind of sticking this into the part of the code that already simulated like waking up and reporting the serial number. The Amiibo. So this is what the read operation looks like. So it's pretty much the same. The console will go through the same series of steps every time it's doing a read or every time it's doing writing. So this is what a typical read looks like. It wakes up the Amiibo, it reads out some settings, and then it will actually start to read all of the blocks of memory from the storage. So the first, and I would go down this list and basically implement the commands one by one. So the first one is called get version, and all that does is get for each version of ntag, it has its own like version bytes, and all you have to do is send back the exact bytes that mean ntag 215. But one of the first two issues I ran into with doing this, even though these are very simple commands, everything that you send has to have a checksum value sent with it. So in this case, you'll have to calculate the CRC16 checksum on the data you're going to send back. But also, you have a time limit. So there's this the specification for ntag says like for most of these commands, you only have 5 milliseconds to respond. So including like getting the command, interpreting it, and like making a response, then doing a checksum and sending it back. You have to do it in less than 5 milliseconds, or it's going to reset and it's not going to work. So that's kind of why you need the specialized hardware like a Proxmark to do this, where they have very fast dedicated hardware to handle all this. But what I had to do is for these kind of initial commands is add them to a cache where I kind of pre-calculated all the checksums, and then when I would get the command, I could send the cached response back, and then I wouldn't time out right at the beginning. The next part to do, there was this read command, and the read command is just going to read 16 bytes of data from a certain location. And this is where I have to start actually implementing the EEPROM buffer, which one of the things that existed in the code for Proxmark was something called Big Buffer, and it's like this. It's a custom heap implementation. But in addition to like allocating, deallocating memory, it has this reserved section on the heap where you can put the card, the tag data, and you can like free everything else, but still retain that tag data across your different operations. So I took that, and I also set it up so I could send data from my laptop to the Proxmark over USB and store it in the buffer, and also read data back out over USB later. So if I have some Amiibo image, I want to send it in there, I can populate that, and it will simulate that. And then I want to get the state of it back. I can download it back off the Proxmark. So the next command is the fast read, which is it can read an arbitrary range of the pages. Pages are just 4-byte blocks of data. And so it takes the start position and end position. You calculate the checksum, return all those bytes. The write command will update 4 bytes at a certain location. There's the password authentication command. So one of the security features on the end tag is there's the write pages, or writing to pages can be locked unless you supply a certain password, and if you give the wrong password too many times, it permanently locks out those pages, and you can never write new data to them again after that. So for simulating, I don't really care if the console tells me the right password or not. I can just always accept it. But if I want, I still wanted to know like how this worked and like how I could figure out what the correct password was. And one of the nice things I can do with the Proxmark is I can kind of send arbitrary serial numbers when the console tries to wake up the Amiibo. And I noticed if I just put in all zeros in the serial number, I get this weird password back that's just AA55, AA55. That's just the alternating pattern of 0 and 1 bits. And if I put like if I start to put the same value into my serial number, I get back zeros instead of whatever was there originally. So like I put in the AA, the first one gets zeroed out. I put in 55, the first 2 bytes of the password are now 0. So this looks like it's XOR again, because you XOR the same thing against itself, you get 0. Or if you XOR, you get 0 against 0, you get the same thing. And so what I did next was instead of sending zeros, I just put this FF byte at different locations in the serial number. And then I take out that AA55 mask. You can just see the byte from the serial number is getting copied directly into the password until like the 3rd position, where there's actually this shadowing copy of that byte. So then if I mess around and I set more bytes to FF, I can actually, if I put 2 positions ahead, I zero out the FF that had showed up. If I put 2 positions behind, I zero out the other one. And I can doing this, figure out, you can figure out the algorithm for this pretty easily. So it just goes through this process of XORing different bytes in the serial number, and that's how it's going to generate these passwords for any Amiibo. Okay, and then the last part was kind of just integrating the crypto with the simulator. So to do that, the Proxmark client actually has a Lua built into it, so decided I could set up all my logic for like fuzzing and stuff and handling the Amiibo in Lua, because it's a lot easier to write than C, and the kind of overall design of it looks like this. So on the client side, I have the Lua script where you can put your fuzzing logic, and also you can call the ME tool to do encryption or decryption for you, and then you send whatever you want to simulate, you send it over USB to the simulator that's on the Proxmark firmware. And if when you want to get the new state of the simulator, you can read that buffer back out, the EEPROM buffer back out over USB. So that's the simulator is done, and it worked fine on the 3DS. But as soon as the Switch came out, and I tried using it on the Switch, it didn't really work so well. So part of the issue was that the antenna, you want the dimensions of the antenna to be pretty similar to the dimensions of the tag, and on the 3DS. So and the default antenna you get with Proxmark is kind of shaped like an ID card. And that happens to be good for the 3DS because the antenna in the 3DS is also kind of shaped like a ID card and it's similar size. But the Switch, there's this little antenna that's like the size of your fingertip. So you get a very bad signal trying to use the big ID card sized antenna. The official guide for like making your own antenna is you take a bunch of enamel wire and wrap it around hundreds of times and then manually like unwrap it until it's tuned correctly. And I didn't want to do that, so I tried to just buy like these pre-made antennas that were kind of like the right size that looked like this. But I didn't have any background in electrical engineering, so I had to find out why that doesn't work. You can't, the antenna has to be tuned to the entire circuit, and I'm not going to go too much into it, but an NFC antenna is basically a circuit with an inductor and a capacitor, and they have to be matched up just the right way to have a certain resonant frequency, and you want the resonant frequency to be the frequency you're communicating on, and that's on NFC, that's 13.56 megahertz. So because of the capacitor that was on the capacitor they had on the Proxmark was set up, it was tuned with the antenna it came with. To use the antenna that I had, I would need different capacitance to match that, and I had gone through figuring out how do I get the capacitance to be correct, so you can calculate using your capacitance and the property of the antenna, figure out what the resonant frequency is, and I had about 6 megahertz with that thing that I bought, and then to figure out okay, I can add more capacitors to try to get it into the correct range. So it's kind of hard to. It turns out the capacitors you use for high frequency radio, they're very tiny and not I would probably have to make a custom designed circuit board to use those. So back to square one with taking an enamel wire and manually tuning it. But I did try to splice in this crappy 10 picofarad capacitor and see if which is kind of close to what I needed. And it did sort of work with the Amiibo, but it didn't work with the Switch. It's not a capacitor that's designed for RF. So the last thing, there was this signature check. Another feature of these N tags is they have a signature on them that proves NXP Semiconductor made them, and it's a elliptic curve digital signature. And the idea, part of the idea is if you were to either simulate or you wanted to produce your own tag, you wouldn't be able to create a valid serial number and signature unless you had NXP's private key. Which means that I can't just, because the newer console actually checks the signature, I can't just use any serial number I want to unless I know what the signature is. And that's kind of a problem because some games like the Breath of the Wild will limit how often you can use a certain Amiibo, and they limit it, they'll say you can only use it once per day, and they limit it based on the serial number, and that's bad if I want to try hundreds of different inputs. So because of the signature, it seems like I'm not going to be able to just do whatever serial number I wanted. But then I started to try to see what can I do to mess around with this. I did wonder how some of those cheat devices you get at GameStop would do it, and I'm not sure. So I didn't actually look into it too much, but I know that because every Amiibo you use with them, you're sending all your data to their server. They can collect serial numbers and signatures from you, which is not something I'd be able to recreate. I tried to look for kind of crypto implementation errors. So with this, yeah. Oh yeah, sorry. So one of the things that you can screw up with this elliptic curve signature is if there's a nonce value that you're only supposed to use once per signature, and if you reuse it, you leak your private key out. So this happened with the PlayStation 3 game signatures. I checked if they had done this, and with the small set of Amiibo that I checked, they hadn't reused this nonce. But finally, I looked over, actually messing around with the protocol of when the console tries to read the Amiibo. And this is the whole process it's going to go through. It finds, it gets the tag's ID, it reads the signature out, and then it's going to validate the ID of the signature. And finally, it's going to read out all the data, check the HMAC signatures, and make sure that the HMAC signatures are correct. So the problem here is when they validate the ID with the ID signature, and then afterwards they check the HMAC on the data, they never correlate the ID in the data with the ID that it checked at the beginning of this process. So at the start of it, you can give whatever known serial number and signature you have. Like, so if you know just one pair of like a serial number and its signature, you send that first. But then when you actually respond to the read commands, you send data for any other Amiibo with a different serial number. So doing that, so that was the way to get around this. I reported it to them, and they finally patched it on version 5. But they said that there was no way to fix it on the Wii U, which I found kind of interesting. But so now finally I can send like arbitrary, whatever data I want to the console, and I'll try to go quickly through a. Yeah, the video is not. Oh, okay. Let's see. Okay. I can't move this. Okay, so this is on the bottom. You can see the client where I'm running a script to load an Amiibo image into the Proxmark, and then on the top, you actually see the switch. So and because this antenna isn't great, it takes a little while sometimes. But then it showed up. And here I'm going to enter like a nickname and save it. And I would show like loading it up again to show that it saved that it's like the data is persisting in the simulator, but I kind of want to skip ahead to. And then I showed it on the 3DS in the same session because it's cross-compatible. Oh. And finally, I use it in the Breath of the Wild game, where using a certain Amiibo that's like harder to buy now, you can get like this horse. Yeah. So okay. So that's there. So I don't know if there's any time for questions. One or two. Okay. Thanks. All right. Are there any questions?
So I guess the question that I would have is going in and doing the fuzzing after this. Did you find anything interesting after that?
Oh, right. So that at that point, that was like where I stopped up. So the next step is actually like now I have this working tool and I want to start simulating the data. The issue is that the new games on the Switch added a new layer of encryption onto the game data. So like Splatoon 2, for example, even though I could read all the other parts of the Amiibo, like all the game data has a new layer of encryption. And what I wanted to do is figure out how that works, but that couldn't really do that until the Switch was jailbroken and you could decrypt the game. But I think the people that actually made some of the first jailbreaks for the Switch have already actually looked at Splatoon 2, and they figured out what that encryption is. So I had kind of moved on like to doing a different project after it, but all the source code for so if you have a Proxmark 3, I put all the source code up on GitHub and try to get to show the link. So this is all on GitHub, and you know Proxmark's kind of expensive, but if you have it, you can like take this code and try it out yourself. And so, you know, now that somebody's figured out the Splatoon 2 crypto, I think you could try messing around with that. But so I guess that's it. Thank you.